It's a little bit shaky, but please let me know if this is helpful at all. So what I have up here is a scanned document of one of the practice problems you have. If you want to follow along, it's in your blue lab manual, and it should be in page 122. And the equation I put down below is referencing page 121. And the reason why I use it is that with any titrations, you have to know that it always uses a chemical equation. So please follow along. Everything is pretty much, I'll follow through except maybe one or two additional things. Okay, so let's begin. So the example is, suppose 13.25 mils of 0.2203 molarity of KMnO4 were required to titrate a sample of iron oxalate. How many grams of oxalate were titrated? So, two things that you have to notice is that the only clues that you have is the volume and also the molarity. Now the first things first, you want to know about your givens. So we know that molarity, the units of molarity are in moles per liters. Now what we're going to do first is to find the moles of our potassium permanganate. And how we do that is by multiplying the volume by a molarity, but there's some things you have to know first. So I'm going to use my volume of molarity, or my volume of permanganate. So it's 13.25 mils. Now because the units are liters, I want to convert it to liters. They already did it for you in the thing, but I'll do it for you guys. And this is KMN. I'm doing this kind of shortened because it's a little bit hard to write in this, but you guys get the point. So for every 1,000 milliliters of KMN, there is 1 liter of KMN. And then you want to multiply by the molarity. So using the 0.2203 molarity, it will be 0.2203 moles of KMN to 1 liter of that solution of KMN. Now, because we're doing dimensional analysis, you want to see whether or not your units cancel out and you get the right units. So these mils will cancel out, and then these liters will cancel out to get moles of KMN. And your final answer would be 2.919 times 10 to the negative third moles of KMnO4. Okay? So that's the first step. Now the next step we want to do is find our moles of oxalate. So our moles of oxalate, or also known as C2O4. So given our previous value, which is beforehand 2.919 times 10 to the negative third moles of KMN. Now, I want to emphasize one thing. Even though they directly convert from the 2 to the 5, which is based off of this equation, what we actually solve for is the entire compound, which is potassium permanganate. In all technicality, you need to convert from KMnO4 to the permanganate, because even though this is a perfectly, a perfect 1-to-1 reaction, it actually, in other cases, this ratio is against the ions, not a compound to an ion. So we have that, the KMnO4 to MnO4, and then you want to convert from that ratio. So you see this 2 ratio against this 5 ratio. So you want to then multiply by 2 moles of MnO4 to the 5 moles of oxalate, C2O4, to get the mole ratio or the molar value of your oxalate. So again, you see the moles of potassium permanganate cancel out, the moles of the manganate ion cancel out, and you'll get moles of C2O4, and that answer will be 7.297 times 10 to the negative third moles. Now, you want to get your grams of oxalate, and what you want to do to get your grams of oxalate is you want to multiply by the molecular weight of oxalate. Now the molecular weight is equal to 88.02 grams per mole. So we're going to get that previously solved problem, which is the 7.297. So 7.297 times 10 negative third moles. Oh, I forgot to put C2O4. I'm very picky about this. I definitely want to see what types of moles are. And you want to multiply that by the molecular weight. So 88.02 grams C2O4 by the moles of C2O4. You'll see that cancels out. You'll get that value. And in the end, you will get a molar value of 0.6423 grams of C2O4. Okay? So there's everything that they said in the actual pamphlet. I'll show you something that you're expected to know, but they don't actually put down. So one of the things that you guys also have to solve for is the experimental weight percent. Now the experimental weight percent is the grams of oxalate over the grams of the coordination compound that you weighed, okay, times 100%. So you'll be using that previous value that we have over here on the very top. I think it's 6423. And then on the bottom is whatever mass you weighed out. Okay? So that's what you do to solve for the experimental weight percent. Now, for theoretical weight percent, and this is very important to know, you guys. I think a lot of times when people talk about theoretical weight percent, what you've seen is that they multiply, they're like, oh, we just have the molecular weight of oxalate divided by the molecular weight of the coordination compound times 100, and that's your answer. No, that is definitely not it at all. Oops. Anyways, so your coordination compound is FeC2O4, right? Now, for every 1 mole of FeC2O4, you can see there are 3 moles of your C2O4. Now, theoretical weight percent is the same as experimental, but you're using the formula weight to see what it actually is. So we know it's a 3-to-1 ratio. Now you want to multiply it by their molecular weight with their molar ratio. So as I mentioned before, this one's 88.02 grams of oxalate, C2O4, divided by 1 mole. And then this one, which I haven't given you yet, it's a little bit tight, but that one will be 319.90 moles of that compound. I can't write down the units, it's running out of space, but over 1 mole of that compound. So as you can see, at the very top portion, this will cancel out to get your grams of C2O4, and the bottom one will cancel out to get your